I'll show my mum
Good evening and welcome to Birkbeck Science Week. And this evening we have 4 half-hour talks from colleagues in Earth and Planetary Sciences. My name is Nick Keep, I'm the Executive Dean of the School of Science. And basically the 2 half-hour talks, we then have half an hour or so of refreshments out in the foyer, and then we have 2 more half-hour talks covering a range of topics in planetary science. And so our first talk this evening is from Dr Grindrod. Peter did his first degree in planetary science at UCL and then a PhD about volcanoes on Venus. He then stayed at UCL for a few more years as a postdoc and a fellow, and in 2013 moved to Birkbeck as a fellow and lecturer in planetary science. His focus has now moved from Venus to Mars, and he's recently helped to make the first ordnance survey map of Mars. So without further ado, I'll pass over to Peter, who's going to be talking about selecting the landing site for the 2018 ExoMars Rover.
Hello, good afternoon. Can you hear me okay? Is that microphone okay? So what I'd like to do today is to share some of the work we've been doing over the last 2 years or so in helping the European Space Agency try and decide where to land the first European rover on Mars, which is going in 2018 and is called ExoMars. So this is the rover, an artist's rendition of what the rover will look like on the surface of Mars. But what I want to point out to you on the first slide is that, you know, I'm just a small part of quite a large team in the UK. We came together as a consortium very quickly to try and amass our expertise. And the good thing about this group of people is that over half of them are actually students, PhD students and some undergraduate students as well, that have carried out not just the bulk of the work that might be a bit monotonous sometimes, but actually have carried out some of the work that is very important and has actually been fed through to all of the other landing site teams. All of the other landing site teams around Europe, and also the engineering teams at ESA as well. And so there are 4 scientific objectives of this rover mission, but by far and away the most important one is the first one on this list: to search for signs of past and present life on Mars. This is a huge goal to try and set, and it's the one that has the most control about where we want to land on the surface, because we want to try and maximise the chance of success in finding life, so we have to make sure it goes to the right place on Mars. We could find a very safe place to land on Mars. We could almost guarantee the rover will touch down successfully, but we probably won't be able to guarantee or even give you a chance of finding life. So we have to try and balance the two. So this mission will launch, fingers crossed, in 2018, May 2018. There is a backup date that used to be mentioned in brackets. For some of the talks I've been to recently, it's no longer in brackets. It's now given as an alternative option, 2020, so there might be a 2-year delay. So it might go in 2020. It's going to go on a Proton rocket. So this is with a joint collaboration with the Russian Space Agency. Sorry, this keeps going off. I don't know why. This rocket, the Proton rockets, has an 89% success rate, which sounds pretty good for a rocket launch, but I always try and say that if you were to get a plane that had an 11% chance of failure, you'd probably think twice about getting on there. So our precious rover is at the top of this rocket. It did actually launch the precursor ExoMars mission about 3 weeks ago. You might have seen it in the news. This is an orbiter, which is going to take high-resolution images of the surface and be a communications relay for when the rover gets there in either 2019 or 2021. It'll touch down on the surface. Unlike Curiosity, rather than having a sky crane and a dangling on cords, this is going back a generation. It's going to use parachutes high in the atmosphere and then retro rockets. They're going to slow it down, it'll touch down on the surface, and then the rover will drive off the top of the platform once the whole thing is stabilised over a few days. The important thing to remember here is that the rover mission is only supposed to last 218 sols, or Martian days. This is because it's solar powered, it's not nuclear powered like Curiosity. So you don't have an awful lot of time to do a lot of driving. So in terms of the geology, you want to find the best geological outcrops to use your drill to access the subsurface to find evidence of life. But we're not going to have a long time to drive around looking for the best location. So one of the things we need to know is whether we can land on the targets that we want to drill into. And so there are many instruments on the rover. These are all the instruments that are on the rover. The one that we're most interested in is PanCam, which is this twin camera system up on the mast, which is being led by the UK, by the Mullard Space Science Laboratory. We'll fix that later. And so this is part of the instrument payload that Birkbeck is directly involved in, and I play a small part, and we have PhD students and postdocs and other members of the staff that have helped lead the development of this instrument. And so we do things like take PanCam out, this is an emulator of the camera system, take it out to Iceland in this case, to Mars analog regions, places that we think are very similar to the surface of Mars, the best we can do. And in this case, it's a calibration chart, and we're trying to do some geochemical analyses of the rock with this camera, which is actually just designed to take context images. We're trying to push the science as far as we can go and actually use this camera to help select regions where the rover will drill. And this is a mock-up at Airbus Defence and Space, I think it's called now, in Stevenage. This is testing the navigation software, but these are the wheels that will be on ExoMars. We're a lot smaller than the wheels on the Curiosity rover, which are more like 0.5 metre in diameter. These are going back to, say, more like 20 centimetres. So the smaller, and this was a movie that could show you it moving very slowly on the surface, but I want you to remember those small wheels because it becomes important later on. So I can't talk to you about where we're going to land on Mars without giving you a little bit of background on the geology of Mars. This is a map of the whole of Mars showing the elevation, the height, effectively, of the surface, going from the North Pole to the South Pole, and the full range of longitude. And so the blue, purple areas, the white areas are the lowest areas on Mars, and the greens, the oranges, up to the kind of brown oranges here, are the highest regions on Mars. So some of you might be familiar with this map. It's used a lot, it's very important, it's told us a lot. We have huge impact basins like the Hellas impact basin. We have the huge volcanic province of Tharsis, and the Tharsis volcanoes, and the famous Olympus Mons volcano, the biggest volcano in the solar system. And the picture that's emerged over the last 10 or 15 years or so is that you can see the northern hemisphere of Mars looks much flatter, smoother, fewer round features or impact craters in the southern hemisphere. In fact, the latest database shows about 400,000 craters greater than a kilometre on the surface. They're well preserved. And there are more in the southern hemisphere than the northern hemisphere. And so, to a first order, we think that the southern hemisphere is older than the northern hemisphere. It's preserved more of those craters that formed early in Mars' history. And in fact, if you combine that with the geological units in the surface, you can separate the surface out into three main time periods of formation. So down at the bottom here you have the Earth's geological time scale from the present day here all the way back to pretty much the formation of the Earth 4.5 billion years ago. And above there you have Mars' geological time scale. We have the oldest period, it's called the Noachian, which is represented in blue on this map. And those mostly occur in the southern hemisphere. We have this green Hesperian unit, which tends to occur in between the blue and the middle one, which is the Amazonian, the orange one, which represents about the last 3.1 billion years of Mars' history. Now, the interesting thing that we've learned recently is that we can tie the age and the geological units to the geochemistry on the surface as well. And so these locations show the small areas that aren't covered in dust that we've been able to actually understand the chemistry of the rocks from orbit using spectrometers. And it ties in with this story quite nicely. What we've seen is that the chemistry of the rocks during the Noachian tend to be a group of minerals called phyllosilicates, or clay minerals. We have clays on the Earth. The Noachian rocks tend to contain these clays. The Hesperian rocks in the middle of Mars' history tend to contain rocks that are actually sulfates. We're familiar with these on the Earth as well. Things like gypsum, you might have heard of, or Epsom salts. These are sulfate minerals. And since then, during the Amazonian, actually, the chemistry of the rocks is dry, it's anhydrous, ferric oxide is basically a rusty sort of surface. Now this is interesting for the story of life, of where we should be looking for life on the surface of Mars, because we know on the Earth that clay minerals, these phyllosilicates, tend to form when you have water interacting with rocks, but that water is neutral in pH, which is kind of friendly for any life there. Sulfate minerals tend to form when you have less water around, but also that water is acidic in pH, which is less habitable, less friendly for life. So we think we've seen this transition on Mars, and lots of other lines of evidence support this idea that Mars was probably more habitable early in its history, at the earliest part, for say 500 million years, maybe 1 billion years. Then it became less habitable during the middle period, and then since then it's been this kind of frozen, dry, oxidizing environment, not good for life. So, when we're talking about where to go on Mars, we need to go where we found clay minerals and old rocks. Okay, that's my entire Birkbeck Introductory to Planetary Geology course in about 5 minutes. We should still come along for the full story. As scientists, we got given a big handbook, actually, of requirements that we need to meet in proposing a landing site. You don't need to read these. Basically, the main ones are what I just said. It has to be old. This is the first time that any landing site had to be older than 3.6 billion years. That was actually specified, so that really, really made it a tough task. There has to be signs of aqueous activity. This is basically water. This is like other ones. There had to be many sedimentary rock outcrops. The drill on ExoMars can only drill into soft sedimentary rocks, and they have to be close to the rover, which we can't drive very far. They have to be distributed, and there must be little dust coverage as well, because that means the rover will be covered in dust. We can also work out the chemistry of the rocks as well. And it got worse. We got given a whole list of engineering constraints as well. And I'm not going to even talk through these ones, other than to say one of the most important ones is that because of planetary protection protocols, we're not allowed to land ExoMars in regions that are called a Mars special region. So this is anywhere where life from the Earth might be able to actually survive or even thrive. So basically it's places where it's above freezing, there is a chance of liquid water. So that would rule out the very interesting regions that we've just found on Mars about 4 years ago, where you can see these dark streaks in this river of the crater growing in the summer on Mars and then retreating over winter, which are now thought to be salty water. So this is liquid water thought to be on the surface of Mars today. We're not sure, but that's the best idea at the moment. So we won't be allowed to land anywhere like this. Okay, so we're targeting regions where life could have thrived in the past, but it won't do very well today. Okay, so let's bring all this together. Here we've got that great map of Mars again. Here we've got my pie chart. I can't resist doing a pie chart. We've got 100% of the surface available to us at first, which is about the same as the Earth's continental landmass. You know, because we have the oceans, the surface area that we have to explore on Mars is about the same as the Earth. So the first landing constraint is that the parachute needs long enough to slow down in the atmosphere, so you need to land as low as possible in the thickest part of the atmosphere. So that rules out anywhere above -2 kilometres, and it rules out, we've only got 59% of the planet left to us now. The next one is we have a latitude constraint, which is partly through the communications. We get better passes from the orbiters near the equator, but it's also a thermal constraint. The rover will get too cold if it goes near the poles and won't have enough solar power, but also in the southern hemisphere, because of the way that Mars's summers work, the southern hemisphere summer gets too hot for the ExoMars rover, ironically. So it has to land within this narrow band of latitude. And then finally, because of that age constraint, the first time it's been applied, we have to land on the very oldest terrain. We're down now to 2% of the planet that we could consider as being scientifically interesting. The final thing that we have to consider is that landing on Mars isn't a pinpoint process. There is a certain probability of landing within your target area, and the uncertainty in that probability is called the landing ellipse. And so for ExoMars, it's quite a big ellipse. It's 104 kilometres by 19 kilometres. More than that, we have to consider the two different launch dates, 2018 and 2020. Depending on when you launch, in that launch window, means that you'll come in at a different angle. So we have to consider not just a large ellipse, but a whole range of angles for this ellipse as well. So to put that into scale of how hard that task actually is, if we were to land ExoMars in the most habitable part of the solar system, the northwest of England, you would see that just on this landing ellipse, we've got an equal chance of landing anywhere in this ellipse. You end up in Liverpool, all the way over to Sheffield, down into the Peak District, almost touching in Blackpool as well. So this is a huge area you've got to try and find out. It's interesting scientifically, the whole of that ellipse. This is a tough task. Nonetheless, let me talk you through what we did. We have the previous landing sites, although it looks like it, none of these actually are in our green areas. So that's one thing to note. We are landing in regions that will be new. At the end of 2014, our UK group came together after 1 month's notice internally we could find 28 locations on Mars. We could physically put those ellipses down. That was it, basically. We then had a couple of months to work on them before we went to a workshop where 8 proposals were submitted by scientists throughout Europe with some collaborators in the UK as well. We proposed 2 of those 8 official proposals, and then we discussed them at a landing site workshop in 2014. After that workshop, 4 were chosen as the final 4 to be considered. And we were pleased to say that R2, Hapanis Alice and Aaron Dawson made it through to the final 4. They were then discussed at another landing site workshop towards the end of 2015. And then this is the first time I've given this talk since this has happened. It broke because I don't want to do it. In September 2015, the decision was made to go from 4 sites to 1 site, which was Oxyplanum. But there were also 2 backup sites if the mission launches in 2020. This is a bit confusing. If the rover launches in 2018, it'll go to Oxyplanum. There are no backup sites. If it launches in 2020, there's a chance it could go to a backup site, which is going to be one of those 2 sites, Marthalis or Aaron Dawson. And so I want to quickly just take you through what a couple of these sites look like. So this is all the final 4 sites in context. This area covers about the size of Western Europe, which has a huge geological diversity, so we'd expect, the same sort of diversity and complexity on Mars as well. If we take a look at Oxyplanum, which is the chosen landing site, this is a height map again. You can see that there's a high region towards the east and the southeast, and it gets lower towards the northwest. And we've actually seen very old drainage networks. These are all dried up riverbeds flowing in that direction, and they seem to end in that red area, which is where the landing ellipse has been put for Oxyplanum. So there's a chance here that some of these river networks actually deposited material at the end of the channels like they do on Earth. So this could represent the end of a river drainage network. There could be a delta in this region, or just fans of sedimentary material. That's great for concentrating fine-grained material, sedimentary rocks, which is what we need to drill. But actually the reason that Oxyplanum has been chosen is because of the geochemistry. These images from orbit basically show that there's a stack of not just one type, but many different types of clay minerals in Oxyplanum. Some of them are about 100 metres thick, some of them are about 10 metres thick, they change in composition, but all of this ties in with the idea that there was probably groundwater in this region altering the rocks in situ. The problem is that we don't exactly know how these things formed, and also there's an issue with traversability at the prime landing site. This is a zoomed in image now, this is 100 metres, the scale bar. All of these aligned features you can see are small scale wind ripples. So they're not quite dunes, they're small ripples, which aren't a problem to missions like Curiosity, but remember those small wheels? ExoMars will basically be bogged down in things that are this size because its wheels are too small. They will sink into these features. So now industry is analysing whether ExoMars can actually drive through these sorts of terrains, or whether they're going to have to choose one of the backups. So one of the other backups is Marthalis. You can see the proposers spent a long time really trying to squeeze their ellipses into the allowed region, off the black region. They can just about do it, but because Marth is so far north, actually those ellipses have grown, and there's an issue here that Marth might actually be taken off the table because the ellipses are too big. And then finally, the final site that we worked on was originally called Oxypalus. This is not Mars, this is not Oxypalus, this is the River Irwell, which flows through the centre of Manchester out to the Irish coast, to the coast of the Irish Sea. It actually flows through the village I grew up in Lancashire. And so what we did when we proposed this, nobody had studied this site. It didn't even have a name. Oxley Palace is nowhere near, but it's the nearest named feature. So we put in a request to the powers that be to name this thing officially Irwell Vallis, after the River Irwell, because, as we know from this quote, the modern world as we know it was born in southeast Lancashire. And I thought it was apt that ExoMars would find life on Mars, but actually our request was turned down. Not because of the name, but because of the way that things are named on Mars. It was actually called Aaron Dawson. So this feature got named because of our proposal, which is nice, but it would have been better for Irwell Vallis. But this is what Aaron Dawson looks like. This is a perspective view of the main feature. It's basically an inverted river system. A river ran through this area, it dried up, and then other material has been eroded, leaving the river inverted. And we get these things on Earth as well, they're common. This is to show we've done a lot of work on Aaron Dawson. This is the Landing Ellipse. It's safe for elevation. You can see we're landing at the lowest regions, a bit high in the east, but we've convinced the engineers that it's safe. And we've done a lot of new work. There was no geological map of this area at the start, and what we found out is that most of the units that ExoMars will actually encounter, no matter where it lands, it's not going to be more than a few hundred metres away from a deposit that was formed as a result of this river that we think probably flowed this way, down that way, because it's high up here and low down there. And there are many tributaries. We think this thing is one of the oldest river systems we can access on Mars. So obviously we're biased, but we think Aaron Dawson will be a great landing site for ExoMars. And so finally, to wrap up, where now? According to this timeline, which has changed a lot, you can see that it's now early, kind of coming up to, it's April 2016. Originally, by September, the one site should have been approved by the engineers. We don't launch until 2018, but there's going to be no more work done on choosing a landing site between now and then. If it launches in 2020, there'll still be no more work done either, apart from validating one site for the engineers to make sure it can drive through those sites. So, as far as we're aware, the landing site analysis has kind of almost come to an end, unless that one site, Oxyplanum, is proved to not be safe anymore, in which case we'll all go back to work frantically and try and decide which is the best site, because at the moment it's just the safety which is governing which site it goes to. But if it goes back to the two backup sites, it will be a balance between the science and engineering again. And the story that we keep getting told, and that we try and do our best to follow, is that although this is we all work on our own landing sites, the final decision is actually going to be made by ESA and the Russian Space Agency. And it's not a decision that I'd like to make, but when the rover gets there, it's nobody's landing site, it's everybody's landing sites. Not just the people that worked on it, but the people that pay for it through their taxes and through the European Space Agency. So it's everybody's landing site. So I hope that you enjoy wherever it goes. Thank you.
Since the size of the wheels seems to be a really important factor, why are they so small? I mean, large wheels would seem intuitively to be just much more sensible.
There's a couple of reasons, I think. I'm talking about engineers, this is my interpretation. The smaller things are, the less they weigh, which is good for launching into space. So if you can make the wheels small and still drive over things, that's good. To get around the small wheels, what they've done is, there's two things. One of them is that the wheels will actually flex on like a pneumatic tyre would. So they do actually bend as they go over the surface. That should help them not go into sandy surfaces a bit. And the other thing that it could do is, they used to have this technique that no other rover has had called wheel walking. So that if the wheels got stuck and they were just churning on the spot and not actually driving anywhere, they could lock the wheels and then just lift the wheel up and lift it out, and then it basically starts to crawl out, all 6 wheels and crawl itself out of the sand trap. Now, unfortunately, that ability has been taken off and put back on and taken off a few times. And I think the latest is that it will not be wheel walking. I think. So they have tried some things to get around it, but I think it will be more of an issue than it has been for Curiosity. Yeah.
Yep.
You mentioned that several areas on Mars, the vast majority of Mars is off limits because of the fear of the contamination of life forms from Earth. But considering the massive fluctuations in temperature, when the rocket takes off from the Earth and then goes through freezing space and then the solar radiation in the couple of years it takes to get to Mars, will there actually be an Earth-based life form that can exist all of that and then get on Mars and start regenerating?
So this is a really interesting point. I'll rush through the answer for it. I think it's important. So the regions we can't land in are actually quite small compared to the whole of Mars. There's only a few places that are very small. So it's not the whole of Mars, it's just some parts. But in short, basically, yes, there may well be some sort of life that can survive those conditions. And you could say that actually, by sterilising the rover and the instruments to the best that we possibly can, which is, it's not perfect, but it's getting there, we're actually pre-selecting the life that is best suited to surviving the harsh conditions it's about to survive on Earth. We by selection, just send the hardest little things that can survive. We know that things like tardigrades can survive on the outside of the International Space Station, and they basically just close up until they come back into an environment they like, and they'll start to basically live again. So, in short, yes, there are things that could survive in maybe 1, 2, 3 of the conditions we're exposed to, the low temperatures. We know there are extremophiles that can survive the cold temperatures. We know there are extremophiles that can survive the low pressure. And we know there are things that can probably survive the radiation on the surface. But whether there's anything that can survive all of the harsh conditions, I'm not too sure, but I wouldn't be surprised if they could. But yeah, we are basically ruling out the less hardy things and only sending the hardiest things if they survive.
Any more questions?
Yep.
Given the rather dusty nature of the Martian atmosphere, why did you not use an RTG and use solar panels?
Well, it's not me personally, it's the European Space Agency. The European Space Agency builds on its own heritage. So ExoMars has had a tortuous history, it's fair to say. At one point it was actually a joint mission with NASA that would see 2 rovers, and I think one, if not both of those, would have been nuclear powered because NASA has the experience of that. ESA's never had a nuclear powered rover anywhere, so it couldn't basically send it there. It would be testing too many unknowns. It had to test its own nuclear power generating system, RTG, on its own first, and it hasn't done that. So in short, it's because ESA has experience with solar panels. Solar panels have worked very well for other Mars rovers like Spirit and Opportunity. Opportunity is still going now, 12 years after it landed, and it's also only supposed to last 90 days. So, although it's designed to last for 218 sols, the expectation is that it may well last much, much longer because the wind and dust levels can clear those solar panels all the time. So hopefully the solar power shouldn't be too much of an issue.
If the first launch happens to fail, is there a backup for the second launch?
If the first launch fails,
I think you said it's a 10% chance.
yeah,
Right.
don't know, that would be for the ministers of the European Space Agency to decide, and so that would be all the countries that put money into the European Space Agency, whether they would be willing to put more money in to have another mission. My gut instinct is that they wouldn't. It's an expensive mission. It's over €1 billion. Yeah. There's a lot riding on a rocket.
Okay, I'd like to thank Peter very much for that talk. And our next speaker is Professor Hilary Downs. Hilary did her BSc in Durham and her PhD in Leeds. She's just passed 30 years at Birkbeck and is currently the president of the Mineralogical Society. And she's going to be talking about lost worlds